Hello. So let's see. Today the topic is voltage regulation. Voltage regulation. Yeah, so basically how do we create voltages from other voltages on a chip? Let me fix the camera a bit. Yeah, that looks good. Okay. First of all, I just want to justify a bit why we need voltage regulation. How do we use it on a chip? Why don't we just supply externally with the voltage we need? And then introduce the two types of regulators that we use on chip. One is what we call linear, the other is called switched. And those names should be quite literal. But why? So, turns out we get most of the voltages, or the power, or the electrons, or the flow of electrons, or the electric fields from chemical batteries. It's like inside this, this whip. Actually, here you have, inside this whip, you have a lithium-ion battery, and then we charge it from another lithium-ion battery. And when it comes to lithium-ion batteries, the voltage across the cell is actually determined directly by the chemistry. It's related to the chemical potential, or the difference in Fermi levels from one side of the battery to the other side of the battery. And for lithium-ion, well, these rechargeable lithium-ion, they usually go up to about 4.3 volts when we charge them, maybe 4.2, depending a bit on the chemistry. But it is determined by the chemistry, which means that if you pick your battery, the voltage is given. So if you do lithium ferrite sulfur or whatever the ones here are, or different type of primary cells, so non-rechargeable batteries, you can have from 0.8 volts up to 3.6 volts. Now your chip can't necessarily use that voltage directly. And as we all know, we like to plug things into USB, whether it's USB-C or whether it's USB-A or USB micro or whatever they're called. And that power is usually, or the voltage is usually between 4.0 volts and maybe up to 5.5. And then if you have a really long USB cable and you sort of plug it in, the inductance can get you sort of quite high spikes, maybe up to 20 volts. Now, when we look at the integrated circuits, how much voltage the gate oxide can survive is simply a function of distance and the type of material. Now, in 22 nanometers, for example, a quite common voltage is 0.8 volts. If you put more voltage than that on your gate oxide, then your lifetime reduces. Now, back in 180 nanometer, the voltage was 1.8 volts. And it was easier. But for transistors, we just have to make them survive, which means the transistor or the VDD or the supply voltage of the transistor, that's just given for a certain technology. You pick technology and you have a set voltage. You cannot really exceed that by much without really knowing what you're doing and paying careful attention to reliability. On the interface side, so when you hook it up to your Arduino or whatever else you're going to control, things are not moving that fast. Still, we have 5 volt interfaces, we have 3 volt interfaces, which is maybe still the most dominant. There are quite a bit of 1.8 volts and some 1.2 volts, sort of memory interfaces. So on a typical system of chip, you will have multiple voltages, and somebody has to generate those. And that's where voltage regulation comes in. So shown here now is a typical chip and the regulation system. So we have V-bus, that's USB, at the top, usually at 5 volts, and then inside the chip we might have a regulator or a charger that can both drop the voltage down to 4.3 volts and also charge the battery. Now, if you're going to charge a lithium-ion battery, you actually have to get a bit careful, because when you're charging a lithium-ion battery, you have to transition from initially very low current, and then to a constant current charge. And as the voltage increases towards 4.2 or 4.3 volt, you have to go over into a voltage control type of charging. Then, since our transistor cannot survive the 2.5 to 4.3 volt voltage, we have to drop it further. And, well, let's assume that our input-output interface is at 1.8 volts. In that case, we need a regulator, something to take the voltage from 2.5 to 4.3 and then give us a stable 1.8 volts. And on that I/O, we might put our general purpose input-output, our digital input, digital output for the chip. We might put our bias, the band gap. So if we want to create a traditional type of Broca band gap, or just a regular band gap, not the Bamba band gap, sort of the low voltage one, then we need about 1.5 volts and up. So then you run those circuits on that I/O supply. Now, for most of digital circuits, you actually want to run them at as low voltage as possible, because digital circuits have a power relationship given by the frequency times the capacitance times the voltage squared times an activity factor. So it actually scales as the square of the voltage. So reducing voltage on digital cells, if they can run at that voltage at that certain speed, is always best. So there's actually a sort of a power optimum. It's the lowest voltage you can run at the speed that you want is going to give you sort of a optimum power point. So maybe we even want to go lower than 0.8, but assume we're going to run our RISC-V core, because that's open source, you can actually put that on, and you're going to run your ADC. Well, here you can choose. It's not good for analog to digital converters to run at a really low voltage, because the input signal swing becomes so small, and that means that your noise levels become more difficult to handle. And maybe you want to run your radio at 0.8, or maybe you need 1.8 volt there too. But anyway, there is something here in the system that needs different voltages. And maybe they need to be precise also. For example, the voltage that you apply to a digital cell has a huge impact on the timing. So the delay of the digital cell. And as you know, as you should have known, on a chip, you have to know the delay of every single digital cell in all corners, because you want to run a static timing analysis. You have to compute the time from a register where data starts to propagate all the way through the combinatorial logic to the register where the data is supposed to be captured, and you have to make sure that there is sufficient time between the clock edges for the computation to happen. That's setup and hold times. Now, if you change the voltage too much, well, then your timing becomes quite variable. Of course, your threshold voltage will also change quite a bit, so maybe the voltage of VDD is not a big impact, but it's gonna have an impact. Anyway, let's assume you actually need something relatively precise. Relatively precise is plus minus 5%. Pretty okay is plus minus 10. Quite insane is plus minus 1. And plus minus 1% is what you need when you want to charge a battery towards the end of the cycle. And that's quite hard. So, we need regulators. We need something that can take the voltage from a band gap and then generate any voltage from it, from a higher supply, of course. Another interesting topic for system on chips is that the dynamic range of current might be quite huge. So, for example, in most sort of IoT type applications, whether it's your wristband or it's a sensor somewhere, most of the time that device is not doing anything. It's sleeping. And when it's sleeping, you want to use as little current as possible. Now, maybe the battery has an inherent sort of self current of maybe a microamp or something, that it discharges by itself, or maybe it doesn't. Depends on the chemistry. Anyway, if you want to approach sort of a really, really good number, the best would be, I think today, not many chips can go down to 10 nanoamp leakage when off. That's pretty hard. And then maybe when you're transmitting or when you're doing a lot of computation, the current consumption can go all the way up to a few hundred milliamps. Of course, if you're on a CPU inside a computer, we're talking amps, a lot of amps. So the dynamic range of these power subsystems quite significant. I mean, this is sort of 10, 12 bits, 12 bit type of resolution. So it's not easy. So what are the strategies? Here I've copied a slide from Nordic's 5340. This is in the product specification. It's freely available online. And then you can see it has a high VDD-H input. It has a VBus input. It has a VDD input that drives the GPIOs. And then there are some internal power supplies. And there's a few regulators. Now, let's talk about the most straightforward one first. Linear regulators. In a linear regulator, we have a load. This might be our CPU, our ADC, our radio, whatever. And we want to generate a 0.8 volt across that, independent of the load current, relatively independent of the load current. So if the load goes from very high impedance, so high resistance, very low current, to low impedance, high current, then we still want the voltage to stay the same. One way to achieve that is to generate at the input, you generate a input to the OTA, you generate a reference that is the same as your output voltage, you design a fantastic OTA, you drive a PMOS, and the PMOS becomes a voltage controlled current source. So at all times, it tries to adjust the current through the PMOS such that you will get 0.8 volts. Now, of course, in a system like this, you will have a certain bandwidth of the op-amp, which means it can't be infinitely fast. And maybe you have to deliver really fast load transient currents, like to a CPU, which clocks where most of the current is when the clock strikes. But maybe then you add a capacitor to ground and you use that capacitor as a charge storage device to provide the electrons when you have very fast transients. And then you use the feedback loop to provide sort of a slower control of the output voltage. A PMOS is the mobility of PMOS. The mobility of holes is a bit slower than NMOS, which means that you need a larger device to get the same current for a certain overdrive voltage. So it would be better from a size perspective if we could use an NMOS. Now, of course, when I say a size perspective, it depends whether the PMOS in your linear regulator actually matters. I mean, if the op-amp or the capacitor, decoupling capacitor, or the reference ladder or the band gap is a lot larger than the PMOS, then you don't care. If the PMOS is half the size of the chip, which happens, then you care. And then using an NMOS is better. There's a couple other reasons, and I'll direct you to the link in the syllabus that goes on LDOs, which I believe was from Besadrasavi. Anyway, we can use a source follower instead. In this case, we get the same thing as sort of a current, voltage controlled current source, but we're using a source follower, which means that the impedance looking into the source of the NMOS is actually quite a bit lower. And we can deliver more current for a smaller device. A disadvantage of using the NMOS is, well, to turn the NMOS on, we have to have a voltage on the gate that is quite a bit higher than the source. So we have to have a drop. Quite often the PMOS version is called a low dropout because you can have a 1 VDS, a few hundred millivolts, across the drain source, and you'll still have some output impedance, so have some impedance looking into the drain, which gives you a better PSRR, power supply to rejection ratio. For the NMOS, the PSRR is pretty good also, because you're seeing into a really low impedance, the high frequency PSRR. But it has an interesting sort of second order effect, and that is that you are looking into a common gate now. So any noise you have on the load, sort of digital ripple jumping up and down, that will actually be amplified as a current up to the 1.5 volts. So you have to be a bit careful with NMOS source followers, and you have to create that voltage that is quite a bit above the output voltage. But both are fine. One fundamental problem with linear regulators is that I'm pulling whatever I load I have here, I'm pulling the same current from the 1.5 volt, which means if you look at my power consumption, well, let's for the moment say that the 0.8 volt was 1 volt, and we have 10 milliamps, then 10 milliamps I load, then we have 10 milliwatts consumed on the lowest power, or 8 milliwatts for 0.8 volts. However, from the power supply or from the battery, we are consuming the same current, 10 milliamps, but then we multiply it by 1.5. So we're using 15 milliamps from the battery, and maybe even more if it's pulled from a 4.3 volt battery supplying the IO rail, supplying this regulator again. So linear regulators are not good for power efficiency. They are good for noise, low noise, and isolating powers, but not great for power efficiency. I just want to quickly show you that you can navigate to IEEE Explorer, find papers on LDOs, and you can see different ways of designing LDOs. Now, if you had the hope that analog circuits and linear regulators are trivial or easy, then I'm sorry, they're not. No, they're really not. They're quite complicated, and you can use quite a lot of tricks, and quite often the papers use a lot of tricks. But I would encourage you to read the papers, try to understand them, because that's how you get ideas and how you understand more and more about analog circuits. So I recommend go to the papers and read them. Now, switch regulators. So Mouser has this fine, nice overview over the different type of switch regulators. Actually, these are for PCB type of applications. So the step down or buck converter and the step up or boost converter. We have the charge pumps down here in the right corner. I will also encourage you to go to this link and have a look at them. Now, the ones you'll find on this slide, they explain the principle. However, when we actually integrate, for example, a buck, where we use an inductor to store current, and we use switches to charge the inductor to a certain current, then we don't use diodes, because that's a waste. So be aware that although the principle is pretty good as explained in this pamphlet, I would encourage you to read some books on it, or read papers, or actually also the one in the syllabus. There is this paper on bucks. But let me try and explain a little bit how they work. So, oh, wrong way. Yes. Okay, let's start with inductive DC-DC. So, quite common, or most commonly maybe, is to go from high voltage to a low voltage. And what you see in the slide here now is exactly that. Let me find a good, there we go, that's better. We have our VDDH, we have a PMOS switch, and we have an NMOS switch. Then we have an inductor. This is an off-chip inductor. It's not on-chip. It can be on-chip, but it's hard to make inductors, big inductors on-chip. We have the capacitor, which is usually also off-chip. And then we have some form of load, which may be our CPU. The principle of operation in buck DC-DCs is that first you turn on the PMOS. That sets up a current in the inductor, Ix, given by the integral of the voltage across the inductor. So that means it depends on the VDDH and it depends on the output voltage, VO. Actually, it depends on the V1 and the output voltage, VO. Now, the output voltage, that also depends on an integral, the integral of the current through the inductor into the capacitor minus the load current. So this is a non-linear, time-dependent differential equation. I have no idea how to solve this closed form. Might be possible. The tricky part is there's no point in using Laplace, for example, I think, because you have a periodic steady state type of system here. You have sometimes you turn on the PMOS, sometimes you turn on the NMOS. But the principle is you charge the field in the inductor, which sort of sets up a current, or the current sets up a field, and the inductor stores that field such that when you turn off the PMOS and you turn on the NMOS, that current doesn't dissipate immediately. It continues to flow, and it continues to flow in the direction of the arrow. Now, it will continue to flow in that direction until the voltage becomes, until the current becomes 0, and then it'll actually turn around. So, I've made a notebook, a Jupyter notebook, to sort of show you what's going on. Now, I would encourage you before the lecture to try and go through this. You can just open this link. Oh, crap. That was the wrong link. Okay, I need to fix that. I'll fix that in the slides. Anyway, I have it back here. So, here you have the Jupyter Notebook. Now, the Jupyter Notebook, it contains both. You can open that in VS Code, by the way, or you can install Jupyter. It shows the figure. And then what I've done is, instead of trying to do a closed form solution of the differential equations here, I've done it in Python. So I've set up the constants, like the how much time is the PMOS turned on and how much time is the NMOS turned on. And then I have some vectors that I initialize. And then it's a big for loop to run through the equations and compute the currents and the voltages in the system. In this case, I turn on the PMOS when the period, so TS now is my current time, is modulo less than the duty cycle times the time constants, which means that you sort of go high with the PMOS first, and then it goes low for a while, turning on the NMOS, and then it goes high again, according to the duty cycle. dt is just the delta time from the last time step, and then the voltage across the inductor, that's, well, this is just on off. So when the PMOS is 1, then we multiply by VDDH. Minus, this is trying to model the series resistance in either the PMOS or the NMOS. And then the output voltage, that gives us the differential voltage across the inductor. And then we integrate that differential voltage. Here I'm using something called, I think it's called a trapezoidal approximation. Turns out that numerical integration has a sensitivity to time step and floating point accuracy. I'm not a great mathematician for numerical things, but it helps to do the area like a trapezoid. I think this is also why in SPICE you have trap, as in trapezoid, Newton-Raphson integration, I believe. Okay, and then when the PMOS on, I just store the current for the VDD. Calculate the output current, well, that's pretty easy, that's Ohm's law. And the output voltage is then the integral of the current over C. Okay, so when we do that, we can see, actually, let's put in some initial conditions. So let's start with, first of all, initial voltage is 0. And then we're not going to simulate that long. So I have a period of, what's my period? My T, it's 0.1 micro. Okay, so let's simulate for 1 micro. Okay, so let's have a look here. Okay, so here we can see what we're seeing here in blue is the inductor current, the current in the inductor, and IO is, what's that? That's a current in the output. So that's pretty low at the moment. And here it's actually up to about 0.5 amps, but that's because we're ramping from 0 volt. So if I cheat a bit and I put the initial condition closer to where I expect it to be, 0.9 volts, run again. Then we should see, there we go. Okay, so you can see the current in the inductor is increasing linearly, which we would expect, and then it's decreasing, and increasing and decreasing, and increasing and decreasing. And what's going to happen here now is that if I simulate for a bit longer, the average current in the inductor is going to settle to my load current. And here you can see the settling behavior. And let's run it even a bit longer. Now, my output voltage is actually going to be a function of the duty cycle, how long the PMOS is on and then how long the NMOS is on. As you can see down here. So now we have an output voltage of roughly 0.9 volts, and we have the inductor current of 0.9 milliamps, which is the same as the load current roughly. And then we have the most important point about DC-DC converters. So in the LDO, or in the linear regulators, the current pulled from the VDDH, or the VDD, the supply, that was the same as what was running in the load. But here you can see the current in VDD is lower than the current in the load. Actually, when you look at it here, you can see that when we compute the power, so the power consumption on VDD is about 0.96, and the power consumption on the output voltage is about 0.8. So there's a power conversion and not a current or a voltage conversion. Now it's possible to make DC-DC converters with close to maybe 90+% efficiency, and that's why we use them. We can convert power, so voltage times current, on the battery into voltage times current on a low voltage. They're much more efficient. They use our electrons more efficiently. So let me demonstrate that even more. So let's actually change this. Assume still we want, let's change this to 5 volt. 5 volt input, or we're running directly from battery, 4.3 volt. And actually, to make it easier for myself, I'm going to choose 4. And we want 1 volt out. Okay? And to get 1 volt out, I have to use a duty cycle of 1 divided by 4, which is 0.25. And then I run again. By the way, you can reduce the number of points in the simulation if you want more accuracy. Now, you can see that, well, my efficiency drops. The reason my efficiency is not that good is right now it's not that high current. Let's increase the current a bit. Let's see if that makes a difference. And I also have a pretty high series resistance for the switches. There we go. That's better. More ideal efficiency. Okay, so now we're pulling 10 milliamps, but we're only pulling 3 milliamps, or 2.5, from VDD. So the power conversion efficiency from VDD power to 1 volt power is about 95%, which is pretty good. So play around with this Jupyter notebook and figure out how it works, try to understand it. Let's see, let's get back to the slides. Where did I put my slides? There we go. Okay. So if you download the data sheets for NRF5340, which is the Nordic chip, you will see in the hardware descriptions there are inductors. Inductors, capacitors, inductors, capacitors, inductor, capacitor. And then it says DCC-D, DCC, DCC-H. So inside this chip, there is 3 DC-DC converters. And that's one of the reasons why it becomes low power. You only use the energy you need in order to generate the voltage that you need. Now, DC-DC converters can actually run in multiple different modes. What we saw previously here is what we call pulse width modulation. We have a certain width of the pulse turning on the PMOS and a certain off time. Now you can regulate the voltage coming out of the DC-DC converter by changing the duty cycle. So if I measured my output voltage, compared it to a reference, and then change my duty cycle, I could actually create a stable output voltage, almost independent of the input voltage. There is another way to do it, and that's called, well, actually there's multiple ways. There's many, many ways to charge the inductor and create a constant voltage. Another one is called pulse frequency mode, PFM. In the pulse frequency mode, you have a comparator connected to the output that you compare to a reference. When the output drops below the reference voltage, you turn on the comparator. That will turn on the PMOS, set up the field in the inductor, and for a certain amount of time, a constant time, and then when the constant time elapses, then you turn on the NMOS and you wait until the inductor current becomes 0. Now, one way to measure the inductor current becoming 0 is to measure the voltage across the NMOS. That's a very small voltage, so that this 0 cross comparator need to be pretty precise, probably with the auto zeroing or offset compensation. Now the state machine is quite simple. You start in idle, you do nothing until you get my voltage is too low. Then you charge the PMOS, you count for a while, when the count elapses, you turn on the NMOS, and then when the 0 cross triggers, you turn off the NMOS and you go back to idle. Now I've also made a Jupyter notebook for a PFM mode. Let's see if that link works. Nope, doesn't. I'll fix that. So you can also have a look at that PFM mode Jupyter notebook and see how that works. Now in the integration loop, or in the time step loop, I've now set up a state machine. So we have an idle state where my PMOS is off. Now here I've tried to, well, this is pretty, I hacked this together today, so this is a bad way to do it. I'm actually not entirely sure what it does, but it works. I think it just forces the inductor current to become zero after a few iterations. So when our output voltage drops below the reference, we go to the second state and we start a timer. In the second state, state equals 1, we turn on the PMOS, which means that the Vx voltage, the node Vx is then, well, it's still the voltage across the inductor. The voltage across the inductor is going to be VDDH minus a certain series resistance times the current in the inductor minus the output voltage. And then after a certain time has elapsed, given by T-switch, we switch to the last state, where we turn on the NMOS, and the voltage across the inductor is now, well, you have ground on one side, so it's just minus VO. And then when the current drops to 0 or below 0, we transition back to idle. And then you can see, for a very brief moment, we charge the inductor, and then the current goes down to 0 again, and it creates this sort of ramp. This is why it's called pulse frequency mode. It only does something once in a while. The slope that you see on the voltage on the right side here is given by the load current. Right now, my load resistor is 100k. So if I reduce it to 10k, or actually 1k, then I think I maybe should have reduced the number of points. Yeah. And then you see the frequency increases. Now, instead of having a constant frequency, we now have a frequency that varies with load current. That's not always something you want, but sometimes it's okay. So play around with those notebooks, and we'll go more into detail in the lectures. I'll try to convince you and get you to understand that DC-DCs are fantastic and cool. And hopefully you'll get a sense that you have some mastery or some understanding of how they work before you start to read the papers, because papers can be quite complex. I have a link here to a paper of a book. Now, the main point about PVM versus PFM is that PVM is excellent for really high loads because the switching currents, so every time you switch the PMOS and NMOS on and off, you discharge and charge the node on the, let's call it the left side of the inductor. That will have some capacitance, you will have some switching losses, and those matter for a while, but the PVM can deliver a fantastic amount of current very efficiently. But if the load is very low, so if your average current is really, really low, then those switching losses matter. And that's where PFM is better. So it's better for light load scenarios. So it's good to have a DC-DC or buck converter that can transition between pulse width modulation and pulse frequency mode. Here is the DC-DC. This is a very simplified block diagram. I'd encourage you to go and read in the paper how it works. It's not as complicated as it looks. Well, it is, but it's possible to understand it. But now you at least know what PVM and PFM is. Go read in the paper, and please ask questions in the lecture, and I'll happily try and explain it to you. You don't have to go down in voltage. You can go up. So if you have a silver oxide 0.8 volt battery, and you need a 1 volt or you need a 1.5 volts, then you can boost the voltage. You can go from a low voltage to a high voltage. This is great, for example, for thermoelectric generators, which maybe has a voltage across them of a few hundred millivolts, but you want to power a 1.8 volt system. Well, then you have to boost the voltage, and you can do also that with inductors. It's just a slightly different configuration. You have the inductor, and then you set up the current by pulling the NMOS to ground, and then you deliver the current to the load through a PMOS. Same thing. Oh, well, that's the same thing, but slightly same but different. Okay. There are also others. So you don't have to do it with inductors. You can do it with capacitors. So stacking capacitors, or there are a lot of switched regulators, and you'll find them everywhere. And it's important to know about them, especially if you have to design them in the future, because they are everywhere. And one final point, for power supplies, for any type of power system, you have to know what you're going to use it for before you design it. Because if you know that your circuit or everything on your circuit consumes a maximum of 10 milliamps, you don't want to design a DC-DC that is most efficient at 90 milliamps. You have to design it to be most efficient at 10. Which means that the power system is one of the few things that you quite often have to change between different type of chips. So it's a very good skill to know. Okay, bye-bye.